Welcome to Calculus. Today we will investigate differentiating products of two functions, focusing on applying a derivative rule and then proving the rule using the definition of the derivative. We'll take a look at four examples. So we're looking at functions that really are products of two separate functions. So we'll take a look at this first example. It's y equals quantity 2x to the power of 5/4 plus 4 times second quantity 5x squared plus 5. So I can definitely see that this is a product of two different functions. The first one there in the parentheses 2x to the power of 5/4 plus 4, we'll designate that as f of x. Our second function is the 5x squared plus 5, and that we will designate g of x. So we need a rule. Our derivative of these two the product of these two functions isn't simply the derivative of the first times the derivative of the second. So let's see what that rule is. And this is called the product rule of differentiation. And the way that goes is it says if I have a large function, so large f of x, which is the product of two smaller functions, so like we've got here f of x times g of x, the derivative of that large function, so big F prime of x, equals just plain old f of x times the derivative of g of x plus the derivative of f of x times the original function g of x. And that's our product rule in a nutshell. So what we'll do is we'll work on applying it to this situation. We'll look at four different examples, and then we'll come back and say, can we prove that algebraically? Can we prove it using the definition of the derivative? So one thing I see that I need is to find the derivative of each of these f of x and g of x. So we'll do that first. So if f of x is 2x to the power of 5/4 plus 4, the derivative of f of x is going to be, just applying our derivative rules here, leave that coefficient 2, and then x to the power of 5/4, that's the simple power rule. So I'm going to bring down the old power as a coefficient, 5/4 comes down, times x to the power of 5/4 minus 1. And I want to simplify that derivative. So that's 2 times 5/4 is 5 over 2. X to the power of 5/4 minus 1. 5/4 minus 1 is like 5/4 minus 4/4. So that's x to the power of 1/4. I also want to find the derivative of g of x. So similarly, I'm going to apply these simple derivative rules. 5x squared becomes 5 times old power 2 as a coefficient, x to the power of 2 minus 1. And then the derivative of the constant 5 is 0, so plus 0. And again, I'll reduce that down to 10x. So then I just want to take my derivative by substituting in these four different pieces that I have indicated here in my product rule. So we'll start off by saying the derivative of y. So my first substitution here is the original f of x. So that's 2x to the power of 5/4 plus 4. And then it's times the derivative of g of x. So we calculated that to be 10x plus. Now I'm looking at the derivative of f of x. We calculated that to be 5/2 x to the power of 1/4 times the original function g of x. So that second factor in the original product, 5x squared plus 5. And that is a good derivative. Now I do want to simplify that expression. So I want to distribute and then combine like terms so that this is in the form of a polynomial. So I'm going to distribute the 10x to both terms in the original there. So this is now 20. And then x, I need to add my power. So 5/4 plus 1, it's like 5/4 plus 4/4. So that's 9/4. Okay, second distribution, 4 times 10x is 40x. And then I need to also distribute this 5/2 x to the 1/4 through those two terms, 5x squared and 5. First product's going to be 5/2 times 5, so that's 25/2. X to the power, 1/4 plus 2 is 1/4 plus 8/4, so that's 9/4. So I see I've got some like terms here. Go ahead and circle the like terms. We'll combine those in just a moment. Let's find that last product though. 5/2 x to the 1/4 times 5. So that's 25/2 x to the power of 1/4. Finally, I just want to combine those like terms. So 20 plus 25/2 is like 40/2 plus 25/2. So that's 65/2 x to the power of 9/4 plus 40x plus 25/2 x to the power of 1/4. And that is complete. That is the derivative of that original function y. Let's take a look at a second example that involves a power of x that's down in the denominator. So I've got here y equals 4/x to the power of 3 times quantity 5x squared plus 3. We'll start again by identifying what's my f of x, what's my g of x. So f of x is this fraction, 4/x to the power of 3. And I'm going to convert that. I want it to be all on a numerator level. So I can move that x to the power of 3 up by 4 if I make the power of 3 negative. So my f of x here is going to be 4 times x to the power of negative 3. So while I'm here, I'm going to take the derivative of that. I know I need the derivative of f of x. So that's going to be 4 times, bring down the old powers or coefficient, times x to the power of negative 3 minus 1. So the way that'll simplify for the derivative of f of x is negative 12x to the power of negative 4. Let's also identify g of x. So g of x is that polynomial 5x squared plus 3. And then let's also calculate the derivative of g of x. So that's 5 times old power 2 is a coefficient, x to the power of 2 minus 1. Derivative of 3 is 0. And that will simplify as 10x. So now we're ready to substitute into our rule. So the derivative of, if I've got a big function f of x, again, just to write the rule, f of x times g of x, its derivative will be f of x times derivative of g plus derivative of f times original function g. So each of those products has one original, one derivative, and they switch. So let's begin writing the derivative of y. So the first substitution is f of x, the original. So I'm going to call that 4x to the power of negative 3 times the original function g of x, 5x squared plus 3, plus the original the derivative of f of x, which is negative 12x to the power of negative 4. And that is multiplied times the original of g of x. So 5x squared plus 3. And you can see I've actually written this in a way opposite No, that looks great, actually. That follows our rule exactly. So I got turned around, but I'm back. So that's good. At this point, what I need to do with that is I need to distribute and simplify. So, no, I have made a mistake. Do you see my mistake there? And it just highlights how easy it is to get off the labeling, but it helps to label stuff so that I can come back. I put in g of x instead of the derivative of g of x. So we'll quickly fix that. That should be 10x. All right. So good to double check there. But I think we're on point right now. So now what I can do is simplify and reduce. So I need to multiply these terms. So look in here, this is 4x to the power of negative 3 times 10x. So that's going to be 40. And then x to the power, I add those exponents. So negative 3 plus 1 is negative 2. Now I'm going to simplify this second product. So it's a distribution. So negative 12x to the negative 4 power times 5x squared. The coefficient is going to be negative 60. And then add those powers. Negative 4 plus 2 is negative 2. Second distribution, negative 12x to the power of negative 4 times 3. It's going to be negative 36x to the power of negative 4. And I do see that I've got like terms here. So 40x to the power of negative 2 plus negative 60x to the power of negative 2 is going to be negative 20. And at that point, I'm going to return the x squared so that it's got a positive power. So it drops down to the denominator. I'll do the same with the 36x to the power of negative 4. That's minus 36 over x to the power of positive 4. And that is simplified. So again, we just treat the power of x in the denominator as a negative, and then we can move it back down for that final answer so that all the powers are positive. Let's take a look at an example that's a product of a function that includes the base e. So here's our function y equals x times e to the power of x. What we'll see here is that our two functions, f of x and g of x, are much smaller. So f of x is simply x. So the derivative of f of x is going to be, by our rule, for the derivative of the linear parent function, it's just 1. And then g of x is going to be this power e to the power of x. So the natural exponential parent, the derivative of that function is very curious itself. Remember, the derivative of e to the x is e to the x. So again, let's put the rule that helped me out on the last example, make sure I found an error if I had one. So if I've got a function that's g of x, f of x times g of x, its derivative will have the pattern f of x, so the original f, times the derivative of g plus the derivative of f times the original function g. So again, there's my same pattern. So again, I'm going to fill in. So I'm going to start here. Y prime is f of x. So that's my x times the derivative of g. That's e to the x. Plus, now I'm looking at the derivative of f of x, which is just 1, times the original function g, which is also e to the power of x. So simplifying this reduces down to just x e to the x plus e to the power of x. And that is complete. Let's take a look at a final example that involves binomials and the natural exponential e to the power of x. So again, what I want to start by doing is identifying my f of x and g of x. So f of x here is x cubed plus 1. So the derivative of f of x is going to be the old power 3 as a coefficient times x to the power of 3 minus 1 plus the derivative of 1 is 0. So that's 3x squared. Our g of x for this example is e to the x plus 1, which means our derivative of g of x, the derivative of e to the x again is itself, plus the derivative of 1 is 0. So that's simply e to the power of x. Let's get our rule one last time here. So if I've got a big function, f of x is the product of two smaller functions, then its derivative is the original f times derivative of g plus the derivative of f times original g, og. So then let's fill in again. So the derivative of my function y is going to be original f, so that's x cubed plus 1 times the derivative of g, which is, as we calculated, e to the power of x, plus the derivative of f, we calculated that to be 3x squared, times the original g of x, e to the power of x plus 1, og. So then we want to simplify, distribute e to the x through both those terms. So that's going to be x cubed e to the x plus 1 times e to the x is just e to the power of x, plus, and then now I'm going to distribute 3x squared through e to the power of x plus 1. So that's 3x squared e to the power of x plus 3x squared. So at that point, we could probably just leave it. If you wanted to try to organize it so that it's, in a way, descending powers, we could do x to the power of 3 e to the power of x plus move that other term 3x squared e to the power of x, and then plus 3x squared plus e to the power of x. And definitely that's not the only way to write that. That's just one way to organize the four terms in that polynomial. So that's a fourth example. So what we should do at the end here is say, why is that true? Why is this rule, our rule for taking the derivative of a function that I could write as the product of two separate functions? So let's give a go at proving this rule. So let's set this up kind of as a formal algebraic proof. So we'll begin by saying what we'll assume. So let's just suppose that same assumption that we were working with in our examples, that f of x is a big function that equals two smaller functions, small f of x times small g of x. Now, working from that assumption, what I can do is take the derivative of the big function f of x, and I'm going to use the definition of the derivative. So then the derivative of big f of x, so remember our definition is the limit as the distance between my two x values goes to 0, h goes to 0, of big F at x plus h minus big F at x over h. So again, I'm just applying the definition of the derivative to this function that I've assumed I've got. Well, right away, I can see that this is something I can substitute in my two small functions. So this is equivalent to the limit as h approaches 0. Go ahead and draw the fraction over h, but I want to substitute in these smaller functions. So it's going to be f of x plus h times g of x plus h And again, that's just the way I define that original function, big F of x, minus f of x times g of x. So again, I'm just substituting in, once I've written that, the definition of the derivative for the big function, I'm just substituting in those small functions. At this point, we got to incorporate something that's in a way artificial. So I'm going to create a gap here in the middle of my numerator. So let's put our parts in place that we've got, and then we'll say what we're incorporating that's artificial. So it's still the limit as h approaches 0. We kind of need a large fraction, so we'll create it of over h, and the two parts we got are going to become like bookends. So f of x plus h times g of x plus h. Let me zoom to the end here and write minus f of x times g of x. So you can see that gap forming, and what I'm going to place there is basically a sum of 0, but it's two terms that are going to help me write this as two separate limits. So the way I want to incorporate this is it's minus f of x plus h times g of x plus that same thing. So like if I think about what I've done to the numerators, I've added basically a 0, since those are the same expressions, one's negative, one's positive. And algebraically, that's what makes that a legitimate incorporation. So it's something that we're putting there. Now, why do I put that there? I'm going to highlight two terms here in my numerator. So let's get the yellow highlighter. These are the same terms. So what I'm going to do initially is I'm going to factor that out. So again, this is just kind of laying out my strategy at the outset. I'm also going to try, we'll highlight this in blue, to factor out g of x in this second pair. So that's kind of where we're going. I'm going to factor out the yellow term. I'm going to factor out the turquoise terms. And then we're going to split the limit into 2. So kind of a lot of stuff going on for this next step. Let's take it piece by piece. So it's now the limit as h approaches 0 of, I'm going to go ahead and factor out that f of x plus h. And what's left is going to be in brackets here, g of x plus h minus g of x. And then I'm going to close the bracket. We'll write this as one fraction, and then what we'll do is we'll separate it in a moment. So it's plus, I'm going to leave a little space here, and then I'm going to factor out from this second pairing g of x. And then within brackets, what's left there is f at x plus h minus f of x. And currently what I could do is I could put that all as one fraction over h. But then again, what I'm interested in is creating that sum format that we saw in the rule that we used to take the derivative. So what I'm going to do is I'm going to split this into 2 fractions, and I want to take the limit and apply it to both. And then I'm going to distribute the denominator to both as well. So I'm going to put the limit as h approaches 0 for both of those. So again, I've just taken that factored a piece to the side on each and then split the whole fraction into 2. So at this point, I want to take these 2 things that I've factored out. So again, let's highlight them so that we see clearly what's going where. So this piece, I want to move it using my limit properties outside the limit. So as I do that, we can go ahead and do that right now. I need to apply direct substitution for h equals 0. So that becomes f at x plus 0. If I move it outside the limit, I have to apply the h is approaching 0. And that's okay because that's, again, it's just going to be f of x. What's left there is the limit as h approaches 0 of g of x plus h minus g of x over h. And then we'll do something similar with this second limit. I'm going to move g of x. Let's highlight it again in the blue just so that we're tracking it, or the aqua. That g of x, I'm going to pull outside the limit. And it'll just feature there. There's no h with that term, so it just exits the limit as itself. And then times the limit as h approaches 0 of numerator's now f of x plus h minus f of x all over h. So now what you can see is I've got kind of an organization that's starting to look like my product rule. And really, I'm kind of at the very end. What I need to identify is that this limit on the left-hand product there, the limit as h approaches 0 of g of x plus h minus g of x over h. That is the derivative of g of x by definition of derivative. And then if I bring and look at this second limit, the limit as h approaches 0 of f of x plus h minus f of x over h, that's nothing but the derivative of f of x. And then if I just bring my original terms, f of x plus 0 becomes f of x plus g of x. I have it kind of spread out here. It's all there. So what we could just do is kind of condense it down in terms of space. This is now f of x times the derivative of g of x plus, and we'll try to make the color coding uniform, the derivative of f of x. So I'm going to use the commutative property to put the derivative of f first so that I can see that patterning times g of x. And that is, if I bring down this large derivative of f of x, that is my product rule. So as we do with algebraic proofs, we could say case closed by putting the solid square there. So again, a way to indicate the proof is complete. All right, so thanks for joining for this investigation of applying and then here at the end proving the product rule for differentiation. I'm going to let you differentiate your products of functions. See you soon.